Welcome. So let's say you're running an experiment. It's easy enough when you're comparing two things, but what happens when you have three groups, or four, or more? It can get messy fast. In this explainer, we are breaking down the super elegant solution to this problem, analysis of variance, or as you probably know it, ANOVA. Okay, so here's our game plan. First, we're going to dig into why comparing lots of groups is a problem in the first place. Then we'll unpack the brilliant logic behind ANOVA, this whole idea of signal versus noise. After that, we'll roll up our sleeves and walk through the actual calculations, derive the all-important F ratio, and finally figure out what the result actually tells us. All right, first things first, why do we even need a tool like ANOVA? Let's take a closer look at the exact problem it was designed to fix.
You know, comparing two groups is pretty straightforward, right? We've got tools like the t-test that work perfectly for that. But research is rarely that simple. What if you're comparing 3 different advertising campaigns or 4 different drug dosages? Things get complicated.
Now you might be thinking, hey, why don't I just run a bunch of t-tests? Compare group A to B, then A to C, then B to C. The problem is every time you run a test, you have a small chance of finding a difference just by pure luck, what we call a type I error. And if you run a whole bunch of tests, those chances start to add up fast. Your risk of a false positive just skyrockets. ANOVA is the elegant solution that lets us test everyone at once and avoid that trap. And this brings us to the absolutely brilliant solution from Sir Ronald Fisher. Here's the big idea. Instead of comparing the group averages directly, ANOVA takes a totally different approach. It's all about analyzing and comparing different kinds of variation in your data. The name really says it all, doesn't it? Analysis of variance. The whole method is about looking at all the variability in your data and then, very cleverly, sorting it into 2 distinct piles. One pile is the variation that can be explained by the different groups you're testing, and the other is just the random, natural background noise. So here's the core concept. We're comparing 2 things. On one hand, you have the between-group variance. Think of this as your signal. It's the variation caused by whatever you're actually testing. On the other hand, you have the within-group variance. This is your noise, the random natural variation that happens inside any group of people or things. And this is where it all comes together in one beautiful number, the F ratio. It's a really simple idea, actually. You just make a fraction. You put the signal, the variance between the groups, on top, and you put the noise, the variance within the groups, on the bottom. If your signal is way stronger than the noise, you get a big F ratio, and that tells you something real is probably going on. Okay, we've got the why, now let's get into the how. Before we can get to that F ratio, we have to get our raw ingredients ready, and in ANOVA, those ingredients are called the sums of squares. We're going to follow 4 key steps here. We'll start with a little something called a correction term, just to make life easier. Then we'll find the total variation, the variation among our groups, and finally, the variation within our groups. First up is this correction term. Now, don't let the name intimidate you. It's really just a handy little number we calculate right at the start. You just add up every single score you have, square that grand total, and then divide by how many scores there are. It's a bit of prep work that makes all the next steps way, way cleaner. Next up, we calculate the total sum of squares, or SST. This number is our measure of all the variation floating around in our entire dataset, every last bit of it. To get it, you square every single individual score, add all those squares up, and then subtract that correction term we just found. All right, now for the interesting part. We're going to isolate our signal. This is the sum of squares among groups, or SSA. For this, you take the total for each group, square it, and divide by how many are in that group. You do that for all your groups, add those results together, and then, once again, subtract the correction term. And you know what? The last piece of this puzzle is the easiest one. We need to find the noise, the sum of squares within the groups. And since the total variation is just the signal plus the noise, we can find the noise by just subtracting the signal, the SSA, from the total, the SST. Simple as that. Okay, we've got all our ingredients prepped, our sums of squares are ready to go. Now it's time to actually put them together and build that F ratio we've been talking about. But hold on, before we do that, we need to talk about something called degrees of freedom. Think of it as a way to adjust our numbers based on how much data we're working with. For our among group variation, the degrees of freedom is just the number of groups k minus 1. For our within group variation, it's the total number of participants n minus the number of groups.
with those degrees of freedom, we can now calculate our mean squares. And honestly, all this is an average. We take our signal sum of squares and divide it by its degrees of freedom. We do the same thing for our noise. These two new numbers, MSSA and MSSW, are our final polished measures of signal and noise.
And all of these numbers, they fit together so neatly into what's called an ANOVA summary table. This is kind of like the final report card for our analysis. It's the standard way to lay everything out so you can see the whole story at a glance.
And now, the moment we've been building towards. We can finally calculate that F ratio. And it's so simple. We just divide the signal by the noise. That's it. It's our mean square among divided by our mean square within. And that gives us our final F statistic.
Okay, we've got our number. But a number on its own doesn't mean much, right? The final and maybe most important step is to figure out what this F ratio is actually telling us about our data. So here's the completed table for an example. And just look at the numbers for a second. The variation among the groups is super small, only 0.40. But the random noise within the groups is huge. It's 48. This gives us a really, really tiny F ratio of just 0.05.
So how do we know if our F value is big enough to be meaningful? Well, we have to compare it to a benchmark, a critical value that we look up in a statistics table. Using our degrees of freedom, the table tells us we need an F value of at least 3.88 to say something significant is happening. It's like a high jump bar we need to clear. Well, our calculated F value of 0.05, it didn't even make it off the ground. It is way, way smaller than the 3.88 we needed to be. Because of that, we can't reject the null hypothesis. We have to conclude that there's no significant difference between our groups. That little bit of variation we saw was pretty much all random noise.
And this really leads us to the big takeaway about ANOVA. Think of it like a smoke alarm. When it goes off, it tells you there's a fire somewhere in the house. But it doesn't tell you if it's in the kitchen or the bedroom. A significant F ratio tells you there's a real signal somewhere among your groups, but it doesn't tell you where. The next step is always to investigate which specific groups are different. ANOVA finds the smoke, other tests are needed to find the fire.